Okay, have you ever been on a roller coaster and wondered, right at that terrifying peak, what the exact steepness of the track is at that one single instant? Not the average steepness, but the steepness right now. Well, that's the exact mystery we are solving today. And the answer, it turns out, is at the very heart of calculus. I mean, think about it. Finding the slope of a straight line, that's easy. It's just rise over run, right? We all learned that in middle school. But a curve, that's a whole different animal. Its steepness is always in flux. It's changing from one moment to the very next. So how in the world do you pin down the slope at one single point? Take a look at this function right here, 1 over x plus 1. It's this really nice, smooth curve. Now, if I asked you for the slope at, say, this point, right where x equals 2, what would you even say? You can see it's pointing down, so you know it's negative, but how negative exactly? That question, that is the fundamental question of differential calculus. To solve this puzzle, we don't need some kind of mathematical brute force. Nope. We just need a really clever trick. It's an idea that's so simple, but so incredibly powerful that it basically forms the bedrock of all of calculus. So here's the secret. Imagine you have this super-powered magnifying glass. As you zoom in, and I mean really zoom in, on any tiny little piece of a smooth curve, something amazing starts to happen. The curve, it begins to flatten out. And if you zoom in far enough, it becomes completely indistinguishable from a straight line. And hey, we already know how to find the slope of a line. And that, right there, is the entire idea behind the derivative. The derivative is the exact slope of that line you see when you zoom in infinitely close to a single point on the curve. And the mathematical tool that lets us do this infinite zoom, well, that's called a limit. Now, I know what you're thinking. A formula? But don't let this scare you, okay? All this equation is really saying is what we just described with the magnifying glass. It's just the formal instruction manual for calculating the slope between 2 points that are getting infinitely, impossibly close together. It's the math behind the magic. All right, enough with the theory. Let's put this incredible tool to work and see what it can actually do with our original problem. So here's our mission, plain and simple. We need to find the exact slope, the derivative of our function, f of x equals 1 over x plus 1, and we need to find it precisely at the point where x equals 2. So we just take our function and we plug it into that limit definition we just saw. Yeah, there's a little bit of algebra here. You gotta find a common denominator, simplify things, but honestly, it's just a mechanical process. We're just turning the mathematical crank. And after all that, out pops a number, -1/9. That's it. That is the precise, instantaneous slope of our curve at the exact moment x equals 2. No guesswork, no estimating, just a perfect, exact answer. And would you look at that? This picture just illustrates the result perfectly. See that red line? That line has a slope of exactly -1/9, and it just kisses the curve at our point x equals 2, matching its steepness absolutely perfectly. We call this the tangent line, and the derivative is what gave us its exact slope. But here's where it gets really interesting. This powerful tool, it doesn't always work. And to really, truly understand how something works, sometimes you gotta see where it breaks. So let's check out a different function, the absolute value of x. It's just a simple v shape, but notice that point right at the bottom where x equals 0. It's not smooth, is it? It's a sharp, pointy corner. And that is going to be a big problem for our whole zooming in trick. Just think about it for a second. If you tried to draw a tangent line at that sharp point, which way would it even go? You could kind of balance it there like a seesaw. There isn't just one single line that properly represents the slope. Our geometric intuition is basically screaming at us that something is wrong here. And guess what? The math totally confirms what our gut is telling us. When we use our limit formula and we approach that sharp point from the left side, the slope looks like it's -1. But when we come at it from the right side, the slope looks like +1. And that's the key. The answers don't match. The slope from the left is totally different from the slope from the right. So because there's no single agreed-upon slope right at that point, we just say the derivative does not exist there. Our amazing tool fails, and it fails precisely where our intuition told us it would. So what does all this tell us about the kinds of functions we can actually work with? Let's kind of zoom out for a second and look at the bigger picture. This Venn diagram here shows the relationship perfectly. See, to even have a derivative, a function has to be continuous, which just means it has no breaks or jumps. But that's not enough. As we just saw with our v-shape, a function can be continuous, but still have sharp corners where it's not differentiable. So you can think of differentiable functions as a special, smoother group inside the world of continuous functions. Now, as you go deeper into calculus, you're going to see the derivative written in a few different ways. You'll see f prime of x or dy over dx. Don't let it throw you. They're all just different notations, came from different mathematicians, but they all mean the exact same thing, the slope at a single point. When it all comes down to it, this is what you need to remember. The derivative isn't just about the geometry of slopes on a graph. It's a tool. It's a tool for measuring the instantaneous rate of change of, well, of anything. The velocity of a car, the growth of a company, the rate of a chemical reaction, you name it. So, we've figured out a way to measure change. But what's next? What do you think would happen if we used this exact same tool again, but this time to measure how the change itself is changing? What could that possibly tell us? That's a question for another time.